So thank you very much for giving me the chance to present during this webinar. So my name is PJohansson. I'm assistant professor at Chalmers University in the building physics research group. So I've been working with vacuum insulation panels during my PhD. And so I will present here some results from the work that we have been doing here at Chalmers. So I will start with a short introduction to why it's interesting to look at listed buildings and give you two case studies where we used vacuum insulation panels, first on the exterior of a listed building and then on the interior in a laboratory study. So first of all, as in most parts of the European Union, we have a large part of the building stock which was constructed before the 60s. In Sweden, this is around 67% or 47%, sorry, of the building stock. And these are also the buildings with the worst U value of the exterior walls. So if you can retrofit these buildings to reduce the U value of the walls, we can save a lot of energy for heating. And when we look at the performance of different buildings, we see that the extent of the renovation has not decreased the energy use that much. This is a figure showing the energy use for buildings based on the operational energy use in Swedish multifamily buildings. And the blue bars is the buildings that have no renovation reported, and the purple or red ones are the ones with a substantial renovation. And as you can see, most building has not been renovated for energy efficiency measures. There are other measures that are more important than to save energy in the past. So there is still a large possibility to reduce the energy use in the old building stock to the standards of today. As you can see, the energy use is quite similar for all buildings up until 1975, and then it decreases a bit for the newer buildings. And listed buildings is mainly in the city centers of our cities. And these buildings, this is an example of a building in Gothenburg, which was retrofitted in the 70s when they wanted to save energy after the oil crisis. So they installed some insulation on the exterior, and this is how the building looks today. So there is a lot of architectural character and completely changed appearance of the facade with this measure. So now we are working in a project where we want to recreate architectural appearance of the building and to where we do a second renovation, if we can put back the original appearance more or less, or make the building look as it was intended from the start. So many of the listed buildings have protected facades. That means we cannot do anything on the exterior. We have to use interior insulation. In many cases, we have a limited additional wall thickness, so we can't use internal insulation because we lose a lot of the space that we have in the building. And also when we use interior insulation, there is the question what happens with the old construction. This is a brick facade where you see the bricks has been exposed to freezing and thawing, so the brick surface has cracked. So I will show you two examples, one with exterior insulation and one with interior insulation. And in this project, we have used the vacuum insulation panels. Vacuum insulation panel is a material which has a very high thermal performance, or thermal insulation performance. So traditional insulation materials have a thermal conductivity around 30 to 40 milliwatts per meter in Kelvin. And then we have these super insulation materials, which has better thermal conductivity than stagnant air. So we define super insulation as materials that have a thermal conductivity of less than 25 milliwatts per meter in Kelvin. And mainly when we talk about super insulation, we refer to aerogels that were invented around the 1930s and vacuum insulation panels, which might be more feasible to be used in these buildings, since it has a very high thermal performance. And the main advantage is, of course, the limited additional thickness that we need to install in the building, so the wall can remain more or less the same thickness as it was before the retrofits. And the vacuum insulation panels works like this. We have three means of heat transfer through a material. So we have the conduction through the gas, we have the radiation through the porous system, and we have the conduction through the solid matter in the material. And in the vacuum insulation panels is, of course, vacuum, so we reduce the conduction through the gas, and by that we reduce the total thermal conductivity of the material. So this is a high-performance super insulation material, which requires a bit of special treatment at the construction site. So I will show you now the case study. This is a building in Gothenburg from the 1930s. The first floor of the building, or the ground floor of the building, is made of bricks, and the two upper floors are made of homogeneous wood or timber. And in this case study, we used one part of the building as a test wall, where we installed the vacuum insulation panels, and the other wall was used as a reference to compare how the retrofit would influence the heat and moisture performance of the building. So it was now 6 years or 7 years almost since the VIPs were installed in the wall, and since then we have been monitoring the wall with a number of sensors in the facade to make sure that the hydrothermal performance is not at risk. And we're also monitoring the reference wall, and we're also monitoring the outside climate, of course. So here we wanted to obtain a slim construction. We have very high attention to the details. We have the roof to wall connection that should not have been changed because of the listing of the building. We have, when you do the maintenance in the future, we have to make sure that the scaffolding can be installed in the facade, and we also have to protect the facade from water from the outside, of course. So here we used a number of different layers. So this is an elevation of the facade. The red parts are the vacuum insulation panels, and the yellow parts are mineral wool. Since the vacuum insulation panels cannot be cut at the construction site or not punctured by drilling, we have to have another material in between the panels to protect the vacuum panels. So here we use, from the inside, we have a vapor barrier covering the old existing brick and wooden load-bearing construction. On the outside of that, we install these vacuum insulation panels and the mineral wool strips. All of this is then covered with another layer of mineral wool on the outside, as you can see here. The entire exterior is covered to protect the vacuum insulation panels. And then we have an air space or an air gap on the outside before we install the new facade. And as I mentioned, the details are quite of importance here. So we want to maintain the roof overhang from before, and I think we succeeded quite well in this project. while the energy use was reduced by around 20% if this would be done at the entire building. Here we don't have any measured energy use since it's only one of the facades that has been retrofitted in this case study. But as you can see, we still have the distance between the wall and the roof overhang, which the listing requires. So in the next slides, I will show you a laboratory study where we have studied interior insulation. And in this case, we have tried to simulate what happens when we have interior intermediate floors that are connected using timber studs or timber beams in the wall. So we have built a wall in the laboratory. So it's brick and mortar. We have a lot of different relative humidity and moisture content sensors monitoring the hydrothermal conditions in the wall. So this is one of the sensors. From the inside, it looks like this. So we have the intermediate floor connected into the wall with the wooden studs. And then on the inside, we install the vacuum insulation panels to see the influence on the temperature and relative humidity conditions in the wall. So this is basically how the wall looks like. We have the wooden beams inserted into the brick, and then we have the vacuum insulation panels on the inside. And also here we have tried to make as much of the wall covered by vacuum insulation panels as possible. But of course, we cannot cover the parts where we have the intermediate wooden beams and the intermediate floor where it connects to the wall. So here we will have a thermal bridge. And we also have a number of sensors monitoring both in the wall itself at different depths and also in the wooden beams to see the change of the hydrothermal performance in the wooden beams themselves. And these are quite high risk to have an elevated relative humidity and risk for mold growth and dry rot to form in the at the connection space between the wooden beams and the bricks. So this wall was then placed in a large-scale building envelope climate simulator. So we simulate the interior climate and the exterior climate. And we also have control on the not only the temperature and relative humidity, but also on the rain load from the outside. So we can simulate a rain event on the facade. And if we look into the results, I will show you results from the wooden beams in different depths of the wall, or in the wooden beams at different depths. So it gets quite high moisture content in the wall. So already after 1 week, you see here 3 weeks of measurements in 2 locations in the wooden beam surface. So this is 2 wooden beams at the bottom of the wall. And we can see there is no big difference between the 2 positions or the 2 wooden beams. So this is the case without vacuum insulation panels. And when we add the vacuum insulation panels, we see there is not so big difference at the surface. It gets wet as fast as in the case without the vacuum insulation panels. But if we move into position B in the wooden beam, we can see there is another behavior of the relative humidity in the center of the wooden beam. So here we have a much slower response. Of course, the distance that the moisture have to be traveling into the wooden beam by diffusion is delaying the moisture accumulation. And in this case, we can see a quite large effect by the adding of the VIPs on the inside, since we have now a much lower temperature in the wooden beams. So here we have a higher risk for elevated relative humidity in the wooden beams, as you can see on the black curve. So basically, this was the laboratory study results, and basically what we can see is that it behaves as we expected from when we did hygrothermal simulations in calculation tools in advance. This is what we, of course, expected. So another possibilities to use super insulation materials such as vacuum insulation panels is more to cover parts where there are large thermal bridges, like around the windows. We can place the vacuum insulation panels only at these positions to increase the thermal comfort of the building, or of the thermal comfort for the occupants of the building, and not cover the entire facade. So this could be another case that we will look into more in detail in the coming projects that we are working on. So to conclude this talk, we have shown that the vacuum insulation panels can reduce energy use substantially without increasing the thickness of the facade too much. So we can keep the appearance of the building if we use exterior insulation also, if it's not a brick facade or a plaster facade, of course. So in this case, we reached a 20% energy use reduction. We also improved the hygrothermal performance compared to the reference. I didn't show any measurement results here, but since we have exterior insulation, the existing wall gets warmer, and therefore, if we have the same moisture conditions that we had before, the relative humidity will decrease. And then we will have the opposite conditions when we look at the interior insulation, as we saw from the laboratory study. The moisture content increased in the wooden beams when we have vacuum insulation panels compared to when we don't have it. And what we also saw is that it's very important to have knowledge about the properties of the materials that are existing in the wall that we want to retrofit. If you don't have good knowledge and are aware about how the materials behave, then it's not so easy to predict what will happen with the hygrothermal conditions in the wall, and also the energy use, what happens with that. So basically that was my message for today, and I want to thank you very much for listening.